Hello everyone. So welcome to our this week Rigorous Infusion AI seminar. And today we're very glad to have Professor Xuehai Qian to give us this talk. And Professor Qian is currently Associate Professor of the Department of the Computer Science at Purdue University. His research group mainly focuses on developing efficient domain-specific systems and architectures for graph and machine learning. So in the past, he developed scalable and efficient coherence protocols and architectural techniques to support the debugging and enhance programmability of the shared memory parallel programs on multi-cores. And he is the recipient of the many prestigious awards, including like the NSF Career Award and the ASIC Rising Star Award. And his research contributions have been published in the many top architecture system conferences like ISCA Micro, so on. And he has been inducted into the Hall of Fames of all of the top 4 ISCA Micro, HPC, and Espolis architecture conferences. Okay, so now let's welcome Professor Qian to give us this talk.
Okay, thank you for the introduction. So today I want to share our recent research on building the system for graph analytics and machine learning. And it's also on graphs. And so we know that we are in the new golden age of computer architecture, and this term is mentioned 5 years ago by the 2 Turing Award winner here. And the big contest and big picture is that we are facing the high demand to support AI and big data applications. But on the architecture or hardware side, we are facing the end of Moore's law and then scaling. So the viable solution to achieve the good performance and energy efficiency is to explore the vertical integration of application domain-specific like language systems and architecture, and also we should leverage the emerging technologies such as processing and memory. But in this talk, I will be mainly focusing on the system for graphs, and we focus on graph mining and graph learning. So this can be considered as a special case and examples of the domain-specific systems. So we think that the graph is very important because it naturally captures the relationship between entities in the different applications in the real world, such as the web graph, social graph, and the graphs in the scientific research. So in fact, the Communication of ACM published an article several years ago about the importance about the importance of the graph for the future applications and the research. So here I first want to review some basic concepts of the graph, and here you can see an example simple graph, and so the graph. So the information we need to store is the vertex and edges. And so one way to store that is to just store the edge list, which also include the vertex information. And also importantly, the graph can be considered as a matrix. For example, here is the adjacency matrix of the graph, and the non-zeros indicate that there is an edge between the column and the row. So there is an edge between the column and the row vertex. But of course, essentially the graph is sparse. So most of the elements in the matrix are 0, and we do not want to store zeros. So we can also have the adjacency list like this, right? In practice, normally used format is called a compressed sparse row, or CSR, and it's an example of the sparse graph representation. And in this case, we give you an example to store the graph here. And so in the representation, we have 2 arrays. One is N, it's essentially the vertex array. Another is F, it's the edge array. So you can see that the element in the vertex array stores a pointer to the start of the edge list in the edge array. So for example, for the vertex 2, it has 3 neighbors, 1, 6, and 1, 6, and 8, right? 1, 6, and 8. So the edge list contains 3 elements here, and here there is a pointer pointing to that. And it's still 0 because there is no outgoing edge from 1, okay? So here the 3 is the same. It has an edge list of 1, 6, and 7. And so this pointer, if this pointer, you see that the adjacent elements of the pointer are the same, it means that there is like no information, or the edge list is empty. So essentially, it is a concatenated edge list of all the vertex, and here it stores the pointers, and if there is any data associated with the vertex, such as the such as a scalar value in the traditional graph processing, or later in this talk, we can see the feature vector in the graph neural network. It will be logically stored together with the vertex. And so we normally talk about when we access the graph data, we have the challenge of the memory access, or specifically the random data access. So what is the source? First, we can see that to access the elements in the edge list, or essentially all the neighbors, the access is sequential. However, we have two challenges for the two sources for the random access. One is to access the data of the vertex. So for example, if you want to access, so if you want to get the feature vector of a vertex, you need to find the address, and the address is so the address is random. Another thing is that if you want to jump from one edge list to another vertex edge list, you need to have a random access, right? And so another challenge of the graph is the graph partition and communication. And this is mainly to enable the scalability. For scalability, we refer to two concepts. One is to support the large graph, which means that if we have, so if the graph is large and it cannot fit into the memory of a machine, we want to partition that so that each machine can access the data in its memory. Another meaning is that we want to leverage the computing resources for all the machine to achieve the parallelism. So basically, we want to have the application to be scalable with the computing resources and the memory. So we partition the graph, and in this case, we can see that the simple graph is partitioned in over 3 machines, and each machine has a set of has a disjoint set of the vertices here. And also the edges related to the local vertex are stored also in this machine. So due to the graph partition, we have the inter-node communication. There are two kinds. The first kind is to access the remote vertex data or its edge list. For example, here from the machine 2, if we want to access the edge list of 3, 4, and 6, 3, 4 are local, but 6 are the vertex the edge list of 6 is remote. So we need to move the data from this machine to this machine 2. Another kind is the synchronization between the vertex data update. So here, the reason is that there are several edges that cross the machine boundary. And for this, but we also need to enable the local computation in the machine. So for example, for the vertex 3, right, we have the master copy in the machine 2, but we also have the replica in machine 1 and machine 3. The reason is that there is an edge between 0 and 3 in machine 1, and there is an edge between 3 and 5 in machine 3. We want to be able to propagate the information between 0 and 3 and between 3 and 5. So in this case, we have the replica in these two machines. And this kind of a synchronization means that, for example, if some information is propagated to the replica of machine 1, and the replica of machine 3, they will be eventually also aggregated to machine 2, which is a master node. And after it considers all the aggregated information and updates the value in the vertex 3, it will also give back the updated information to the replicas. So this kind of communication is a synchronization. So here we will start with the first application related to the graph. It is a graph pattern mining. Perhaps it is not the same as the traditional graph processing system that you are familiar with. But this introduced more computing. So this application introduced more computing challenges. So the definition of this application is that we have two inputs. One is the input graph here. Another one is a pattern graph. The goal is to enumerate all the subgraphs in the input graph to find the embeddings of the to find the embeddings of the given pattern that is isomorphic. So that is isomorphic to the pattern. Okay, so for example, based on this graph pattern, we have two embeddings of this input graph. The current method is to perform the pattern aware like enumeration. Basically, we want to construct the pattern or construct the embedding from one single vertex, and so gradually we can reach the whole matching of the pattern. And the code pattern is essentially the nested loop. So you can see that we start with the vertex and we look at its neighbors, and also it involves the computation, so which is to intersect with the edge list. And so to match a pattern, there are different ways. Specifically, there are different order to match the different vertices in the pattern graph. And here is one example, A, B, C, D, but we can do that in the different order. In general, this application or computation performs the data movement and also the computation. So first, we want to fetch the edge list, right? Because, for example, we start with one vertex, we need to get the neighbor list so that we can know what to look next. And then when we have the two edge list or more, like during the enumeration, we need to perform the intersection. So specifically, for example, here we have the edge list for vertex 5. Right, and we have the edge list for vertex 4, and we want to perform the intersection to find like a certain embedding. So in this case, the intersection, one of the intersected node is 3, and here we identify a triangle, and then we do another intersection. We do another intersection, we find a 6. So at this point, we can identify the whole pattern. And then we can, so this process can go on, right? So just briefly, we can see that there are data movement and the computation. So we also, so in the recent work, we will not talk about this in this talk in detail, but we proposed architecture support and the instruction set extension to perform the intersection in the graph pattern mining and also in general in the sparse computation that will overcome the CPU inefficiency due to the branches and data dependencies in the tight loop. So the high level idea is that you can have, we can have a special instruction to fetch the streams, which is the sparse data, or for example, the edge list, and then we can use a single instruction to perform that intersection. Okay, so that is the big picture of the graph pattern mining. And then in our system, we focus on the distributed graph pattern mining with partitioned graph. So most of the graph pattern mining systems, they're not based on this. They are not based on the distributed like execution. For example, they assume a graph to be stored in the memory, or they assume the graph to be stored in the like storage. So you can only leverage the computing resources of a single machine. Even if they consider the distributed machines, most of the system support assumes that the graph is replicated in the memory of each machine. So you only take advantage of the computing resources of multiple machines. Fundamentally, if we want to scale with both computer resource and the data resource and the memory resource, we need to have the partition graph, and only one or two systems support that. So the key challenge when we support the graph pattern mining with a partition graph is to support the efficient communication. So specifically to perform the intersection, like we said before, a machine may need to fetch an edge list from a remote machine. So we have seen that is the common behavior for the like partition graph, right? So the intuition is that we need to reuse the data to maximize the value of the fetch list. So we already pay the price to fetch the list from the remote machine, and we want to maximize the value to leverage that, right? So how do we do that? We should, so we can certainly like implement a general like software data cache, right? So for example, in this case, this machine is looking at the enumeration process from the 3 red dots, 3 vertices, right? And we can imagine that we grow the subgraph, which has k hop. The number of hops is depending on the pattern, right? And then during this process, there are data that are overlapped between the different processes, and we can implement the software cache to capture the data reuse. However, the problem is that if you implement the software cache, you need to pay high overhead. For example, you need to manage the data, you need to track the data reuse, for example, the reference counters. And that is fundamentally the exact reason that the current system does not provide the good performance. Okay, so to solve this problem, our solution is to consider the fine-grained parallelism. Specifically, we look at the graph pattern mining, the enumeration process. So here you can see that we start with a single vertex and then we look at its neighbors, right? And so we consider this step as an extension. And then following that, we consider further neighbors. And when we have a two-edge list, we can perform the computation, right? So we essentially consider each extension of one step in the tree as a notion that is called extendable embedding. So we want to consider this as a fundamental primitive for the graph pattern mining because it has a well-defined data and the computation. The data is the computation, which is the intersection needed, right? And the computation is the intersection itself. So for example, if you want to get the edge list to perform that computation, the data may be local, may be remote. And the advantage of this fine-grained approach is that we can schedule the computation and the communication in a decoupled manner. So for example, at one point, we generate extendable embedding that is a task of computation that needs to be performed. However, the data may not be available. So the runtime system can schedule the communication and put the computation on hold. And later, when the communication, when the data arrives, we can schedule the computation. So the responsibility of scheduling the communication and the computation can be decoupled and separately decided by the runtime system. So it enables the flexible support for the different exploration order. In general, at a high level, our system, the distributed execution engine, can be connected to any single machine systems with that abstraction. And the implementer, not the programmer of the application, the implementer of the single machine system can implement the existing logic to match the different patterns in the extend function that is considered to be the interface between these two parts. You can see that the implementation can leverage the extendable embedding to enumerate the whole pattern. Right, and then here we can also implement the execution model in the system to flexibly schedule the computation and the communication. And then after that, we can enable the efficient distributed execution for the graph pattern mining. So here we want to emphasize that in our system, we enable the efficient computation and communication scheduling, specifically because we are looking at traversing the tree from each individual individual vertex, right? To do that, there are different ways. One is BFS. So this case, the black dots indicates the nodes that we have already explored or visited. The red one is the nodes to be visited. So from this BFS, you can see that it provides an ample opportunity to overlap the communication and the computation. However, it consumes high memory assumption, so it consumes the high memory consumption. The other solution is a DFS. So it consumes a fixed amount of memory consumption, but it did not, so it cannot provide efficient communication and computation overlapping. So in our system, we implement the hybrid approach between the BFS and DFS. Basically, we consider the fixed chunk, okay, the fixed chunk in the tree at one level. And we perform the DFS among the chunks, but we can still perform the BFS within the chunk so that we can enjoy the benefit of these two approaches. The important property is that this design provides a bounded memory consumption, okay? And here, this part summarizes the data reuse in our system. We have 3 kinds of data reuse. First kind is between the parent and the child of the nodes in the tree. And this data sharing is directly supported by, so it's directly supported by the data pointers. So we don't have, and the second case is the data sharing inside the chunk. So they are allocated with the same amount of, like with the same areas, of the memory, so they can share the data. In addition, we also implement a static cache without the replacement to control the overhead across all the trays, so that this cache can capture the hot data. In addition, for each chunk, we can also implement the circulant scheduling to efficiently overlap the computation and the communication. So in the evaluation of the system, we evaluate our distributed execution engine with several single machine graph mining systems, and we use 8 nodes and only CPU. So here are the applications that we considered, and also the graph data sets. So they are the different algorithms in the graph pattern mining, and they are the different graphs we use. So the first result here, you can see that is K automine. Automine is the previous work, I think it's a system publishing SOSP 19 on the graph pattern mining. GraphPy is SC20. It's 2 systems. And we incorporate that into our system. So starting with K. Okay, so we enable the distributed execution. We compare with the distributed version of the GraphPy, which is based on replicated graph and the partition graph solution, the Gsyncer. So from the result, we can see that our system significantly improved the performance. And the reason for the Gsyncer being very slow is because of the data cache. And the data sharing does not leverage the property of the algorithm. On the right, you can also see that the breakdown of the execution time, the Gsyncer has a lot of overhead to manage the cache and the communication, but in our system, we can remove that, so we can reduce that overhead significantly, and so the computation efficiency is improved a lot. So in this slide, we also compare our system with single machine systems. So our system is a distributed system, but we can set the number of nodes to 1, right? So we can see that the performance is comparable. It means that our system implementation is efficient, and sometimes we even outperform the other single machine systems, and this is mainly due to the fine-grained parallelism. So last, we want to show the important result to analyze the very large graph in our system. So we are talking about the graph with billions of edges or hundreds of billions of edges. And our system, the evaluation is performed in the 18-node cluster. And so we compare that with a big machine with a big memory. For example, 64 machine with 1 terabyte memory. And you can see that compared with 18 nodes and 1 machine, we achieve 4.5. So we achieve 4.5 speed up. Specifically for the largest graph, and we compare our execution with the native optimized implementation to count the triangle. To count the same number of triangle, our system spend 200 seconds using under 600 cores. However, the state-of-the-art implementation uses more than 6,000 cores, but the execution time is 4 times. So this comparison is to compare with the distributed version of the specific triangle counting application. Okay, so the second part is the deep graph neural network. So we are building a system for the training of such Qian, right? So it's in general, the common Qian that you have seen, maybe it contains a few number of layers. but it's important that the system can support various number of layers. And in fact, the recent work illustrated that so there are many applications for the deep GNNs, such as the GNNs with 16 layers, 32 layers, or even 64 layers. And some of the recent work pointed out that some of the graph problems can be also solved by the GNN. In general, GNN training has two approaches. The first approach is a full graph training, which basically considered all the graph data, and we want to propagate so we want to propagate the feature vector or the embedding information across the different vectors depending on the GNN level or depth. Another approach is sampling-based GNN training, which considers a subset of the graph, and we sample and then basically the two approach is orthogonal. And in this work, we focus on the full graph training, which contains all the graph vertices. And our focus is the communication of the distributed full batch GNN training. Okay, so about the GNN, you may have heard about the general framework called the DGL. That is a very popular system for the GNN training. They also have the distributed version. So it essentially supports the mini batch approach, and it is evoluted from the machine learning community, which means that we want to generate the subgraphs or samples based on the single vertex, and we want to compare, or basically the samples in that system is similar to like an image when you train the normal DNN, right? So we want to claim that the DGL system cannot support the deep GNN for fundamental reason. So the fundamental reason is that the mini batch approach requires that we generate a subgraph with a number of hops, and the hops is depending on the number of layers in the GNN. So the common GNN or the traditional GNN has a few number of layers, like 2 layers, 3 layers. So you can just go to your neighbor and neighbor of neighbor. For example, it's indicated here, right? So it is a small region. But if you talk about the large or deep GNN, right, you need go to many steps, and in the graph data, if you go to more hops, you can easily even take the whole graph. So that is the fundamental reason that the DGL doesn't work with the deep GNN. The second reason is that we can reuse the previous figure because the problem is the same. So if we sample the graph from different vertices, right? And when we increase the number of layers, the sample is larger, and the region of the overlapped vertices, so the region of the overlapped vertices is it's also larger. Previously, we think that if you use the software cache to manage that in the graph pattern mining, it will incur the high overhead. But this is also problematic for the GNN because that region, if you perform the computation for the different samples separately, that region will also incur the redundant communication and computation. Okay, so for this reason, that DGL system cannot support the deep like GNN. So a more feasible way is to support that with a graph parallelism. Okay, graph parallelism, the idea is that we have a graph, right? So that we first partition the graph, like what we mentioned before, and we have the master node, and we have the like the replica here. So the principle is the same as a general graph processing or distributed graph processing. And then during the execution, how do we achieve parallelism? We achieve the parallelism by assigning the GPU with the different graph partition. So for example, here we have 3 GPU, so they have the 3 graph partitions, right? And then they can execute the layer by layer. And so in this setting, we do not care, or the deep or the depth of the GNN has less, so the depth of the GNN has less impact because each layer corresponds to one iteration of the training. So you have 32 layers, then you just run 32 iterations. So if you, after you run all the iterations, forward and backward, it is considered to be an epoch, right? So in this setting, the number of layers is will determine the number of iterations. So it's not a big deal. And the communication here is the communication to synchronize the feature vector, is the communication to synchronize the embeddings of the different vertices among different machines, right? So you can see that we have 4 layers and we need to perform 4 communication like that. So the amount of the communication after the analysis, we found that it is, so the complexity is determined by number of layers, number of the hidden dimension, which is essentially the size of the embedding or the feature vector of each vertex, number of vertex, and also number of GPUs. So this basically is not a scale. So it's not scalable. And here we also does so we also did the experiment to show that. And here you can see the results when we increase the number of GPUs, right? And you can see that the communication amount and the epoch execution time is increasing a lot when we have more GPUs. And this part also shows that a large portion of the execution time is devoted to the communication. Okay, so our solution to solve this problem is to change the setting for the parallelism. The key idea is that we want to have each GPU to be responsible for a subset of consecutive layers. Okay, and so here you can see that we partition the layers, but we replicate the graph in all GPUs. So previous approach, the partition the graph. You may have the lingering question that, oh, how about the graph is so large, you cannot fit into the memory of the GPU. Later, we have the solution. But here, we first assume that the graph is replicated on the GPUs, and we achieve parallelism by asking the GPU to process different layers. In this case, the communication becomes more efficient because first, it incurs less communication. It only occurs at the layer boundaries, and after the analysis, we find that it can reduce the previous communication by a factor of the Qian layers. It also enables a better pattern because the communication is only happening between the specific pair of GPUs, not like in the previous case, like among all the GPUs, right? So based on this idea, we want to build the pipeline training. So the challenge is that by the nature of the GNN training, we need to process the whole graph layer by layer. So the whole graph goes through the first layer, and then we run the second iteration. Whole graph essentially go to the second layer, right? That lacks the parallelism and also increases the GPU utilization. It also impacts the GPU utilization a lot because at any time, only one GPU can be busy. So to solve the problem, we want to partition the graph into the chunks, and so that all the GPU can process the chunk layer by layer in a pipeline manner. So you can look at this figure here. That we have the whole graph. We can consider the whole graph as B1 to B5, right? If you follow the original case, essentially B1, B5 needs to go through the first layer completely, and then the second layer can start at this point, right? So there's a low GPU utilization. With the chunk, we can overlap the forward and backward. But it brings a problem. The problem is that it introduces the inconsistency of embedding vector among the chunks. So for example, the B1, okay, B1 has some neighbor according to the chunk partition in, let's say, B3, right? But when the B1 is at the layer 2, the B3 at layer 1 has not even been executed, right? So in a sense, the B1, so the B3 part has the stale data. So what is the problem? So this will affect the training if you do not care or introduce a special technique. So the idea that we use is that first we allow the staleness in the embedding because this is a fundamental requirement to enable the pipeline execution. However, in the training, so we can take a further look. So in this case, for example, if we consider B2, what is considered to be stale? The stale is a region. So B2, if it has some neighbor in B3, 4, and 5, it's stale. But for the neighbors in B1, B2, it's fresh, right? So for backward, it's the opposite. B4, if it has some neighbor in B5 and B4, it's a fresh. But if it has a neighbor in B1, 2, 3, it's so they are the like stale neighbors. So we introduced 3 training techniques to mitigate the problem of the inconsistency. The first is that before each epoch, right, we want to shuffle the chunks so that each epoch will assume different chunk order, and this avoids systematic bias. The second approach is the second technique is that we want to fix the stale embeddings. So basically, we want to use a range of epochs to use the same so we want to ask a range of epoch to use the same like stale embedding, same version. So for example, for epoch 11 to 20, we all ask them to use the embedding produced by the epoch 10. This improves the consistency. The last technique is to avoid using the stale gradients in the backward propagation. We want to discard the stale gradients of its neighbor. So for example, if some neighbors that is used by B4 are coming from 1 to 3, they are set to 0. But we double the fresh gradients in the for the fresh neighbors to compensate the effect. Okay, so now we want to consider the problem. For example, how about if the graph is so large, it cannot fit into the memory of the GPU? And also we have other reasons. For example, what happens if we want to also support the shallow like Qian, like with 2 layers or 3 layers, but we have 8 GPUs? How do we utilize all the resource? Or if we have very deep Qians, right, that requires the partition of the graph into many chunks. Maybe the 3 techniques that we mentioned before cannot mitigate the effect of the inconsistency due to the deep pipeline. So how to tackle that problem? The solution we find is a hybrid graph and hybrid graph and pipeline parallelism. So basically, we want to allow the partition of the graph among the GPUs in the same way as a graph parallelism, and the same GPU rank in different groups hold the same graph partition. So here you can see that we have 4 graph parallel groups, and 1, 2, they have 2 partitions. 3 and 4, they have the same 2 partitions. And 1, 3, 5, and 7, they have the first partition, the same rank. The other has the second partition. Okay, so here among these 2 is a graph. So it's graph parallelism, and the communication between them is graph. So the communication between them is graph communication, but we still have the pipeline between the groups. So this is what we call the hybrid parallelism. First of all, when we map the task to the GPUs, we should consider the communication intensity. In general, the graph computation is more intensive, so we tend to map the different graph partitions into one node, okay? And between node is pipeline parallelism. So here, the 3 figures summarize the communication amount trade-offs among these 3 options. So as we have already discussed, the graph parallelism introduces communication between before all the layers, and here there is a coefficient called the replication factor. It is the average number of replicates for a vertex, and that determines the communication overhead between the machines. So this is multiplied by the total number of the vertex and also the hidden dimension, right? So for the model parallelism, we already said that we have this communication, okay? This communication, actually, we only have a layer -1 like communication between the layers. This is hybrid, and it's interesting that it can explore the trade-off. So we still have the layer communication, and so we have the replication factor is different, right? Because any different graph partition will have the different parameter for this alpha. Okay, so we have the layer wise communication, and so we have the graph level communication, but we also have the layer communication at this point. Okay, at this point, but we do not have the layer communication inside like this box. Okay, so we have the communication in this way. So essentially, you can calculate the amount of communication after you partition the graph. Okay, so for the evaluation, we use 2 GPU nodes, and each node has 4 GPU. It's not a very high-end GPU because that's very expensive, and also the CPU. And here is internode GPU communication, and here is the intranode GPU communication. So we evaluate the 4 GNN models. 2 of them are not designed for the for the depths, for the deep case. But 2 of them, indeed, they are designed for that. But all of the 4 models can be used to evaluate the performance. And we set the number of layers to 32, and hidden dimension is 100 for small graphs, 1,000 for large graphs. Okay, for the pipeline setting, we partition the 32 layers into 8 stages, 4 layers per stage. Hybrid, we partition that into 4 stage, 2 graph partition, 4 stage. So this is a stage, 2 graph partition. So we have 8 layers per stage. And we use a popular graph partition, so a popular graph partitioner, and these are the graphs we look at. And we also indicate after the partition, what is the replication factor. Yeah. And you can see that this number is very slow because the graph is very sparse. Okay, so here we want to first compare the performance with graph parallelism. You can see that so we indicate 3 tables. Per epoch is the per epoch's training time, communication volume, communication time. So we can see that the pipeline parallelism can improve the performance a lot. And this is due to the reduction of the communication volume and the communication time. For the physics graph that we mentioned before, it is very sparse. So actually, the pipeline is slower than the graph because the computation workload is very light and utilization of the GPU is not very high. And also, you can see that for certain graphs, for certain GNNs, you can actually observe that the reduction of the communication time is even more than the communication volume. That is because of the better communication pattern in our case. It's always between the pair of GPUs. And this result compares with the DGL. DGL, you can see that by running 32 layers, our system is orders of magnitude better. The reason is, as we mentioned, the DGL fundamentally cannot support the deep GNNs. And for this case, it's mainly due to the redundant computation in the overlapped region. And this figure supports this. This figure analyzes scalability. You can see that we use increasing number of GPUs for the different GNNs, right? The same color indicates the same GNN. You can see clearly our solution scales better. And this figure provides the breakdown of the execution time. You can see that here is the baseline graph parallelism. You can see a lot of time is spent in the communication. And in the pipeline, that portion is very small, is drastically reduced, and the hybrid is in between, right? So it is reasonable. If we look at the pipeline, right, or GN pipe, our solution, it reduced the communication time to only under 10%, so it can increase the utilization of the computer resource. There are bubbles in the pipeline, but the bubbles can be further reduced by more advanced pipeline techniques, such as pipe dream. This table indicates the sensitivity in terms of the communication volume when we increase the number of the GNN layers. You can see that basically the data matches our previous complexity analysis. When we increase the number of layers, the graph communication in graph parallelism, the graph communication in the graph parallelism is increasing a lot. It's increasing because there is a factor. So the number of layers is a factor, right? So, but in our case, it stays constant. And this is the reason that when we have deeper GN, so we can have the good speed ups. We also evaluate the usage of the hybrid parallelism by using our system with the shallow GNNs. So we basically have evaluate, I think it is three, maybe two layers, but we still use 8 GNNs, right? We still use 8 like GPUs. So the graph parallelism will partition that into 8 partitions, but in our hybrid, we can have 2 stages with 4 partition for each stage. Okay, and here is the result. You can see that the hybrid system, which incorporate our idea about the pipeline, still outperform the graph parallel, and so this side is hybrid performance. This side is graph parallel performance. So it's better, right? And so it indicate important trade-off of the communication. To compare it to compare the two, you can see that the hybrid introduce the layer level communication, like between the layers, right? But it reduce the graph communication. What is the reason? The reason is that we can have less number of the graph partition and less number of the communication due to the synchronization of the master and the replica. Okay, so lastly, we want to study the efficiency or effectiveness of the proposed training techniques. And here is the overall result. We can see that with the 3 techniques, our system, graph, the 2 GNNs that is designed for the deep case can converge well, and sometimes the final accuracy is even higher. And this figure shows that so what if we don't apply these techniques or apply only a subset of that? Overall, we can see that if we don't apply, the model simply cannot converge. And if we apply only 2 among the 3, the model cannot converge either. So it means that all the techniques are required. Among them, we found that the last technique is the most important one. Okay, so this is the result for the Qian training system. And last, we also started the preliminary study supporting the Qian training on the CPU. So on the GPU in general, the graph training, the aggregation and information propagation is conducted in the matrix view, because we earlier mentioned that graph can be represented by the matrix, right? So we can express this algorithm in the matrix and then call the cuPlus library to conduct the sparse dense matrix multiplication on the CSR format. So the internal implementation of that library will handle data movement inside the GPU memory hierarchy and schedule the computation of tiles on the GPUs. But on the CPU, we do not have that library and the high capability of the computing resource, right? So what is the reason that we want to support the CPU? So we want to use CPU for the Qian training. The reason, the big reason, is that the CPU is much more less expensive, right? So it's more cost effective. So in general, if you can provide the reasonable performance, it's always a good thing. On the CPU, we can see that it can only perform the graph operations in the graph view. Basically, for example, if you want to perform the aggregation from your neighbors, you need to read the feature vector of them and then compute the aggregation and then write the computed result into the destination vertex. So it involves the random read of different feature vectors, relatively simple computation, and the repeated write to the same location. Okay, it's like so it's similar to the accumulation operation when you accelerate a neural network. So that is the whole picture. So in the CPU, if we want to perform this kind of computation, you need to perform in this way. So how can we improve that? So what is the chance? What is the reason that we think it might be possible to close the gap between the CPU and GPU? The common wisdom is that the GPU can provide a massive parallelism, right? So so it must have a much better performance than CPU. However, we counter that intuition because in this kind of application, they are mostly memory bounded, but the GPU is designed for the compute bounded application or compute intensive applications, right? So the GPU performance is likely bottlenecked by the data movement from the GPU memory to compute through its memory hierarchy. So what is the CPU advantage? We believe that the CPU advantage is a large cache in the modern CPU and high memory bandwidth from the cache when you access data from the cache. So for example, in the low-end AMD processor, it has 128 megabytes, 128 megabytes, like level 3 cache. The bandwidth is around 400 gigabytes. High-end, it can even provide more than 1 gigabytes of the L3 library, of the L3 cache. For the GPU we use, it just has a 6 megabytes L2, but high-end GPU, so L2 is larger, but it's not much larger, and the bandwidth is very high. However, the GPU is difficult to exploit the locality due to the constraints of the small L2 and the data parallel execution the data parallel execution model. It means that the high bandwidth cannot help much. And this is, I should point out that this is only true for the memory bounded applications, right? So the GPU is designed mostly for the compute-intensive applications. So at least we believe that for the Qian training, there is an opportunity to use the CPU to close the performance gap. So obviously, to close the performance gap, the key is to explore the locality, right? So it is a very old idea, but we think and found that it's important to improve the Qian training. So the problem with the current or the naive implementation is that we have the imbalanced locality between the read and write. We have multiple read to different feature vectors at different locations, but we repeatedly write into the same location. In the machine learning accelerator jargon, it is similar to the output stationary. And we want to perform the balanced, so we want to achieve more balanced read and write locality to improve the performance. And the idea that we tried is to follow the Hilbert curve to traverse the vertices in the graph. Hilbert curve is essentially a specific order to traverse all the elements in a matrix. It can be generated recursively. For example, you can divide the matrix into 4 parts. We follow this order, and each part is divided into 4. And we can follow the certain order inside the block and connect the paths together. And eventually, for any size of the matrix, we can generate that curve. So graph can be considered as the matrix, right? And it means that we can follow a certain order to traverse all the edges of the graph. And here it indicated that if we follow that order, this can provide a more balanced locality. So essentially, the read locality in this the read locality in the original case is slightly is improved, but the write locality is decreased. So previously we write to just one location repeatedly, right? Then we move on to the next, and here we can write to the different location. So in this case, to implement this idea, we can essentially sort the edge list according to that curve, right? And we can also separate each feature vector into the subvectors, so that we can at any time we can allow more vertices to fit into the cache and improve the chance of the reuse of the data. One caveat is that when we implement that with multi-thread, we actually needs to consider the race or ignore the race. The problem is, for example, different threads may update the same vertex embedding, right? But But in the experiment, we found that if we ignore the race, it does not affect the convergence. And this is consistent with a famous paper nearly 10 years ago from Stanford. Later on, we also want to try to optimize the computation or the aggregation using the SIMD instructions of the CPU. And we performed some preliminary experiment to evaluate the potential of this idea. We compared the CPU execution time with the GPU execution time on 2 nodes. When we conduct the CPU experiment, the GPU are not used. And these are the settings. So we use the same cluster, so the setting is the same as before. And we just implement 2 graphs and 2 partitions and the GCN with 2 layers. And this is the result. So first of all, we want to say that if we ignore the race condition, we found that the convergence is not affected at all. So it means that the race is not very frequent, right? And so we obviously ignoring the race is the way to go. Second, in terms of the overall performance, we can see that. So the blue part is the GPU, and the light green part is the original CPU. So there is a large gap, right? Then, if we just apply the Hilbert curve, and we can also use atomic operation to ensure that so the race is serialized. That performance is the dark green bar. And then if we ignore the race, we can further improve the performance. You can see that importantly, especially in this case, the performance is very close to the GPU. And in fact, we can have more optimization. So we hope that the gap can be reduced further. Okay, so that is just the preliminary result for this part, and we are still working on this idea. Okay, so this reached the end of the talk, and in this talk, we introduced the 3 systems that perform the analytic task, such as the graph pattern mining, or the machine learning task, such as the Qian training on graphs. And we also started a preliminary study of the graph training on the CPUs. So the main takeaway of the talk is that I want to emphasize it's very important to consider the algorithm and the system in a cohesive fashion, so that we can enable the vertical integration of the algorithm and the system in the new golden age of a computer system and architecture. Okay, so that is the end of my talk.
Okay, so thank you, Xuehai. So this is a very, very dense talk and a lot of very important information here. Any questions from our audience? So you can unmute yourself or input a question in the chat box.
Yeah, I have a very quick question. So in your entire setup, you assume that when you run the subgraphs on some separate set of machines. So what does each node of the graph entails? Like, is it a processing node or is it data collection node?
So you're talking about which part?
Just when you mentioned in the beginning, where you have you have like machines. Yeah, here you have distributed the graph into separate machines.
Yes. So can you repeat the question, because I saw that is related to a particular part.
Yeah, so is it like each graph node, is it a separate processing entity itself? Or is it a data collection node?
So node, you refer to the machine, right? Not to the vertex in the graph.
I'm referring to the vertex in the graph.
So the machine, each machine is responsible for the computation for a subset of the vertex of the graph. Yes, for the subset of the vertex and edges in the graph.
Okay.
So exactly for this example, so you can imagine that the machine 1 will update, for example, 0, 1 vertex, the data for the vertex 0 and data for the vertex 1. And that requires the information from the neighbors, right? So that's why we have the replica here. And the machine 2 will update or compute the the data for the vertex 2, 3, 4, and machine 3 will compute the data for vertex 5 and 6.
Okay.
Yeah.
Okay, thanks.
Other questions from our audience? So actually, I have some questions. If nobody ask questions, may I?
Yeah.
I ask. So first, so Xuehai, I remember in one of your slides you mentioned that for the overall diagram of that for the different nodes and the partition for the graph. I remember.
Mm.
And
so it's about which part?
I see.
Maybe you can just say your question and I will try to answer.
I remember, so in one of your slides, so your system is arranged that so there are 2 nodes and each node have like this 4 GPUs
Oh, yeah.
Yeah, that's it. Yeah. No. I think the previous
This one.
this one. Yeah. So here, you mentioned that like the graph level communication that is occurs between the GPUs in the same node, right? And the layer level communication.
No. So the graph level communication in this particular example is the communication indicated by the blue arrows.
Yeah. That is within
Because in this case, one node has 4 GPUs, but because of the hybrid organization we chose, the graph communication happens between 1, 2, and between 3, 4.
Yeah.
Between 5, 6, and 7, 8.
Okay. And my question is that, so here, like between the 2 nodes, the communication is a layer level communication, right?
Layer, yes, layer.
And we know that the kind of the communication speed between the different nodes that is kind of much slower than the communication within
yeah,
node.
exactly.
So my question is why here you arrange that the layer level communication happens that between each nodes instead of that we let the graph level communication that is on the between the two.
Right. So that is a very good question. Actually, you can see the slides here. You can so you can range the logical hybrid parallelism in any way you want. And for example, this is slightly different from the previous, but in this case, I think we have 4 graph partitions, 2 stages, for example, right? So you can, for example, have 4 graph partitions in the same node among the 4 GPUs, or you can have this organization. And we claim that this organization and configuration is not good because the communication between the node, as you said, has a lower bound width, right? So why we do that? Because according to this part, the graph communication is more intensive than the layer communication, right? So we have a factor that is replication factor here. Okay, so if you partition that into 4, or any number of the graph partition, we have the replication factor. And the total amount of the communication in this case is alpha times V times H, okay? But the layer level communication, there is no factor. It is a V times H. And you can see the reason from here, okay? So in this case, the layer level communication between the layers is a fixed number. So it's a V times H. But the graph here, there is a factor, and the factor is determined by the partition. And in fact, in the result, you can actually see that the factor is mostly larger than 1. So it's like 2. So in this case, it means that this is roughly 2 times as this, or more than 2 times. But for very sparse graph, this can be slightly lower than 1, right? So that is the reason why for the physics graph, it is so the So the graph parallelism is actually slightly better.
Okay.
Yeah.
Yeah,
You can
thank you
see
very
these
much
two
for pointing
numbers.
it out. So I was wondering, so
Yeah.
some kind of difference that is also depends on like the what type of the GNN model you use.
No, I think this is a function of the graph partition. So if you change a graph partitioner, that factor may be different. Yeah, and if you change the number of nodes, that factor is different. In general, this factor is affected by the graph partition, but it's increased. It's increased when you have more number of nodes.
Okay, I see, I understand. So then I have a kind of the natural follow-up question. So from the perspective of the design automation, so whether do you think it's possible that we can derive a kind of the automatic decision framework that can determine?
Yeah, actually, we didn't mention that. So when you decide how which scheme to choose, you actually a very important thing you look at is a partition. So you can imagine that you have a partitioner and you can try different choices and you can select one proper one that has the lowest communication.
Okay, I see.
Actually, it's possible. It's not. It's. I think it is even independent with the GNN model. It's related to the graph.
Yeah.
Of course, the number of the iterations or for example, how many layers is determined by the GNN model.
Okay, I see. And I have another follow-up question. So your last part of the work on the potential replacing the GPU using the CPU for the GN training is very interesting. So actually here you mentioned that because the GPU that is mainly designed for the computation bound application, right? And but for the GN, as you indicated, that is kind of more memory bound. So then a natural question is that, so we know that for many like non-graph neural, but the deep neural work, like the transformer, we know that in many cases that they're also kind of the memory bound, right? So in that case, do you think whether it is possible that the CPU can still play a kind of the more important role?
I think yeah, we are also looking at that. The CPU, we think that the gap between the CPU and GPU would be, I think if you want to use, okay, first of all, yes, that is, so it's memory bound, but it's not as memory bound as a graph, right? So here, the important thing is that we need to access the graph data, right? So I would say that this one is more memory bound than that. So the transformer, like that you mentioned. In fact, compared to the traditional graph like processing, like a PageRank or shortest path, the GNN training is less memory bound than that. The reason is that the computation involved here in the aggregation is more than the simple operation in the traditional, like in the traditional graph processing. The problem is, for example, here, at least we have a vector, right? We have a vector. So the communication amount is more. And in the graph processing, this part is simply, for example, addition or comparison. So it is very simple. So that is more memory bound. So compared to the case that you mentioned, the GNN training has higher memory, is more memory bound because of the graph data. So because of the graph data access. However, we also think that maybe CPU can be used for that purpose, but it's only true if the model is sparse. For example, it's quantized and it's, like it's tuned. And in addition, we should also use the special instructions in the CPU to support that sparse computation. I think if we use this tool, it may be possible to close a gap, but I think there is still a gap.
Okay, I see. Thank you.
Yeah.
Any other questions from the audience?
Hi, this is Xiang. Actually, I have one question. So in one of your slides, you mentioned you are using multiple GPUs to do the training for for multiple in charge of multiple layers instead of partial layers, right? So
in this one.
yeah, I just wonder, for example, for the GPU2, so what will be the input of GPU2? Is it parallel processing among different GPUs, or you have
so
GPU2 has
GPU2,
to
the
wait?
input.
Yeah,
the GPU2, yes, exactly. Okay, so you're talking about a very good question. So GPU2, the input is the embedding produced by the GPU1. So it's it's essential activations like in the DNN, but it's embeddings, right? So essentially, you can see each node or each vertex in the graph has a feature vector or embedding vector. So that's the reason why the communication is the V times H. What you are talking about is that, yes, by the Qian training algorithm, the whole graph needs to go through the first GPU and then produce that embedding and then go through a second GPU, right? So basically, according to the original thing, if you consider B1, B2 toward B5 is the whole graph, actually this part, it cannot be overlapped with that, right? So it's so it basically means that B1 to B5 goes through first layer, and then after that B1 of the second layer start here, and then third. So there's no overlap, right? So that is obviously a problem, and there's no reason that can provide any performance advantage. That is the reason why we partition the graph further into the chunk, so that it's similar to, I think, for example, you send a packet in the network, you partition that into fleet, right? So that a different part can be overlapped. In fact, this technique is already considered for the normal DNN training, which is, for example, G-pipe or pipe dream. But the important difference is that in that case, the different training samples are independent, like different pictures. And so you don't need to care about the dependency. In our case, although conceptually we can use the existing very classical idea to partition that whole work into small chunks and overlap them, but there is an implication. The implication is the inconsistency when you read the embeddings as input from the previous GPU among the different chunks. Some of them are fresh, some of them are stale.
Thank you.
Okay, so other questions from the audience? Okay, then I have one more last question. Yeah. So Xuehai, so in your today's talk, you talk about that like the solutions based on the GPU and also based on CPU. And I was wondering, so whether or how about your opinion about that we design kind of more domain-specific architecture that for the graph processing or for the more specific Qian training or the inference. We know that there are already a lot of works that are published in the top conferences. And how about your vision for these directions? Because at the beginning of slides, you also mentioned that so we need for the vertical integrations with the domestic system or domain-specific language and architecture. Because right now, it seems that so the mainstream solution is still based on either use the CPU or the GPU, right?
Yeah, it's a very good question. So my opinion is that the mainstream solution, and also my opinion is that we should leverage the current hardware, existing like a commodity hardware. So it's maybe different people have different opinions, but I think no matter how the current architecture is designed, it's an example of architecture, right? So so your approach fundamentally it is okay, we redesign the hardware or architecture based on applications. But sometimes I think we have not extracted the most potential from the existing hardware, and the existing hardware always has the advantage that you can directly run the real applications, do the large experiment, and actually different application can directly use that in reality, right? So my opinion is that we should first use the leverage. So we should first leverage the existing hardware, And then, but in this process, we can identify the different problems. For example, here, there is a bottleneck, so there is no way that the existing hardware can solve this problem. Then we can provide some input, right? But in my opinion, we should maybe spend more time in thinking about using existing hardware to build the system before we directly propose something that requires different hardware. That is my opinion.
Thank you very much for that. So because what I think that as we compare to the current hardware support for the graph and the hardware support for the machine learning.
Yeah.
We know that, so
yeah.
there's a lot of many solutions, also the commercial solutions or the startups that for both the cloud or the edge processing of those the deep learning workloads. But for the graph, no matter the graph processing of the GNNs, it looks like the kind of the new solutions are not kind of the so rich as compared to the machine learning hardware. So using this is because that typically for the graph processing that is run on the cloud end, so there's kind of no specific demand.
Actually, yeah, I don't know the other people's opinion, but in general, I think graph processing the application, I think it is much less application or like workload running currently compared to the machine learning. So that's the reason why, as you can see, I gradually work more on the machine learning. But so for that reason, I think that is part of the reason why less people are designing the specialized hardware for the graph, because the demand is less than the machine. So the demand is less than the machine learning, right?
Okay, thank you.
Yeah.
I think there's another question in the chat box. Can you see that?
Yeah, let me see. One more question. Does your graph system support GNN training on streaming graphs or dynamic graph with update? Yeah, so currently the system supports the static graph. So you have the graph here and you learn the embeddings. So you learn the model. I think to support the dynamic graphs, you can always, for example, you can accumulate a certain update, right? And then you can apply this update and the graph is changed, and then you can run a few iterations or few epochs to update the model. So it's possible.
Thank you.
Because I think in a sense that the evolving like a stream graph or dynamic graph is less a problem for the GNN training than the traditional graph processing. The traditional graph processing, for example, if you want to find the shortest path, and if the graph is updated, then your previous answer may not be valid immediately, right? But currently we are talking about GNN, so if you update the graph, you can still, so of course, if you want to reflect the update, you can train the model for several more epochs, right? But that requires several, so that requires processing the whole graph several times. And your previous model is not completely incorrect. So I think if the graph is updated, you can further train, or you can schedule that train in certain manner, or you can schedule that training step in certain fashion, and update the model.
Thank you.
Okay, so let's thank Professor Qian again. So thank you very much for your very wonderful talk, and also thank everyone to attend our this week regular simplification seminar. And please note that our next seminar talk will be 2 weeks later, the October 24, and see you guys next week. Okay, thank you, Xuehai. Thank you.
Thank you so much.
Okay, see you.
Have a good
Thank
day.
you.
Bye-bye.
Bye.